Okay, what we're going to do is we're going to talk about the rest of chapter 6.1. When are things statistically significant? All right. Even though, read this sentence right here. So even though randomization eliminates systematic differences between groups, there's still a chance. There'll still be chance differences. So we should insist on differences on the response so large that it is unlikely to happen just because of chance variation. So statistical significance is an observed effect so large that it would rarely occur by chance is called statistically significant. For instance, when you have those who had whenever you had those who had the sickle cell anemia, because it went from the ones with the placebo had a reaction or had a pain, experienced pain 4.5 times, as opposed to those with the hydroxyurea who experienced it 2.5 times. To them, dropping down would from 2.8 to 2.5 or 4.5 to 2.5, that's a big enough difference. And that's what it's saying down here. Basically, when you have an episode of 2.5 compared to 4.5, that's a big difference. So that's important enough to the people. So therefore, that is statistically significant. All right, the next thing we're going to talk about is how to live with observational studies. Now, does attending church lengthen one's life? Do doctors discriminate against women in treating heart disease? Does talking on a cell phone while driving increase the risk of an accident or having an accident? All right, so people can't be randomly assigned to attend church because going to religious services is an expression of beliefs or absences. We can't use random digits to assign heart disease to patients, to men or women, and we can't assign people to talk on cell phones and drive in traffic because that's too risky. That's an ethics issue. So as it says here, the best data we have about these and other cause and effect questions come from observational studies. Now, we know that an observational study is weak at best. But good observational studies are far from worthless. What makes a good observational study? Well, there's two things. First of all, good studies are comparative. Even when they're not experiments, as long as they're comparative, they're great. They compare random samples of people who do and who don't attend religious services. That we compare how doctors treat men and women patients. So we can often combine comparison with matching in creating a group. When you match certain elements, certain variables, then you basically take those variables out of play. And so this next screen is like pregnancy and painkillers, okay? What we want to do is to see the effects of a painkiller during pregnancy. We're going to compare women who used the painkillers with women who did not use the painkillers while pregnant. From a large pool of women, we're going to take women who did not take the drug. We're going to select individuals who match the drug group. So those who took the painkillers during pregnancy, we're going to record their age, their education, the number of children they have, and some other lurking variables. Well, out of the large pool of women who did not take the painkillers, we're going to select individuals who match those women. So that's what we're talking about, matching. All right, comparison does not eliminate confounding. All right, comparison does not eliminate these confounding variables. People who attend church or a synagogue, they might take better care of themselves than non-attenders. They're less likely to smoke and more likely to exercise. So a direct comparison of ages at deaths of attenders and non-attenders would confound any effect of religion with the effects of healthy living. So a good comparative study, as it adheres in green, measures and adjusts for confounding variables. So if you read here in purple, if we measure weight, smoking, and exercise, there are statistical techniques that reduce the effects of these variables on length of life. So what we have left is just religion itself. So when you match up these variables, what you're doing is you're actually taking those variables out of the equation, whereas the only thing you have left, hopefully, is the religion. You can compare the religion and life expectancy. Next is living longer through religion. Okay, when you see something like where it says even health behaviors were taken into account, what that means is that the final results were adjusted for differences between the two groups, and adjustment reduced the advantage of religion, but still left a large benefit. So basically, we're taking those other behaviors into account. So we're matching those up. All right. Now, sex bias and treating heart disease. Are women discriminated against amongst doctors? Well, if you read here, women tend to develop heart disease much later than men, so that female heart patients are older and often have other health problems. That might explain why doctors proceed more cautiously in treating them. So this is a case for a comparative study with statistical adjustment for the effects of confounding variables. In other words, you have, because the women are older and they have these other issues, you've got to be aware of and adjust for those variables. Okay? And finally, as example 6.7 suggests, statistical adjustment is tricky. Randomization creates groups that are similar in all variables, known and unknown. Matching and adjustment, on the other hand, can't work with variables the study didn't think of. So if there are other variables we didn't think of during an experiment, then those things might eventually hurt what we're trying to do. If you believe that the researcher thought of everything, you should be a bit skeptical. Okay, so if you read this little statement right here, this may be the best we can get, and we should thank statistics for making such wisdom possible, but we end up longing for the clarity of a good experiment, as it says. All right, and I believe this is the last thing. This is the summary. So to summarize everything, statistical studies often try to show that changing one variable causes changes in another variable. That's your explanatory variable, and changing another variable is the responsive variable. In an experiment, we actually set the explanatory variable ourselves rather than observing. And finally, observational studies and one-track experiments open yourself up for confounding with lurking variables and making it impossible to say whether the effect of what the effect of the treatment was. So you got to take care of those confounding and lurking variables. All right, the remedy is to use the remedy is to use a randomized comparative experiment that compares 2 or more treatments. So you have to have at least 2 in order to compare. Otherwise, it's a one-track experiment. In green here, it says use chance to decide which subjects get treatment. So you want to randomize your subjects, and control, you want to have a control group for lurking variables. So either have a placebo or a proven medicine that's out there, and use enough subjects so that the effects of the chance variation between the groups are small. So you want to make sure that you have enough subjects. Those are the 3 things: randomization, control, and large enough groups. Comparing 2 or more treatments helps avoid the placebo effect because it will act on all the treatment groups. And the difference is, so if they are so large that they would rarely happen just by chance, that's statistically significant. So the other thing is, observational studies of cause and effect questions are more impressive if they compare matched groups. So if you match the group up like they did with the women in the painkillers, then it's more impressive. And measure as many lurking variables as possible to allow statistical adjustment. Now, observational studies remain a weak second best to experiments, so you need to know that. So experiments are usually the best way to compare 2 items.